Okay, perfect. So hello, everyone. Thank you for joining this webinar. So this webinar is done in the context of the EUROfusion. So today we welcome Nvidia. Thank you very much for joining, guys. And we will have a view of Nvidia's roadmap on hardware, software, and applications. Please go ahead.
Thank you, Franz, to invite us. My name is Gabriele Paciucci. I'm a solution architect at Nvidia. Today, we will have some update for you guys regarding our strategy, in particular on software. Francois will guide us across all the innovation that we have in our software framework. Then I will discuss with you about innovation in our hardware. In particular, we will focus our super chip that will be available in 2023. And then Filippo will finish talking about the hardware ecosystem, why it's important for us, and what we are doing since 2019 in this respect. So if you have any question, please ask. We are more than happy to discuss with you any of the topic. And I let Francois start to share his slide and update us on the software side.
Thank you, Gabriele. Okay. I will. Do you see my screen?
Yes.
Okay.
It's not full screen mode though.
No, not yet. So I'm switching mode. Where is that? Ah, always fighting with slideshow. Come on, guy. Now you should see it in full screen mode, I guess. Okay, let me do this. Okay, so I will speak for the beginning about our software. I will present you the new thing, the new direction in terms of software development. So in this presentation, I will focus mainly about I would say our language approach, and I will not speak here for them about our tools because we have a very rich software ecosystem tools. So this could be for further presentation or further discussion. Oops, why it doesn't want to swoop? Sorry. Trying to have to go to the next slide. Ah, okay. You have to strike the key very strongly. And I want first to recall for some of you a very important software feature which we call the unified memory. So which helps a lot when you are developing applications or porting application on our platform. So what is unified memory? So simply you have a virtual address space where you could where a pointer could be the reference whatever the object lies on the system. Could be on the CPU or could be on the GPU. And so this and the way it works, it's a combination of hardware, of course, and software. So using the on the system side, on the CPU side, the memory manager of the Linux kernel, and working with our driver. And what does that mean? So that, for instance, you have this virtual space covering both the CPU memory and the GPU memory, and this will enable you to use larger objects than you have physical memory on the GPU. And the way the unified memory is working is on demand. That means that if the object is not, the data is not on the GPU, the data will be moved, or the object will be moved to the, we will see in the next minute how it will be moved. And Gabriele will go even further for the next architecture generation, how it could be done as well. But simply you have to remember that now you could have, and you could manipulate arrays, structures which are much larger than the memory you have on one GPU or on several GPU. And of course, this feature, when you want to use your application on an heterogeneous system, so on a CPU plus an accelerator with a GPU, sometimes you need to tune your application for performance, and we have APIs to do from prefetching, for instance. And how things are working, so just to highlight this feature, and this feature, of course, could be used by the application through the compiler, and we will see in coming slides how. So for this small example here, just to highlight the point, so we need to use a special memory allocator just to say that the structure here, this is a small array, will be using the what we call managed memory or unified memory. So very often you will hear about managed. So managed memory, this is using the unified memory feature. So how does that work? So here we are allocating the array. So, and in fact we are allocating the structure, but we are not filling up the array. Then, and it is done both on the CPU and GPU side. Here with MedSet, you see we are filling up, initializing the content of the array. And here we will launch a kernel, you see, with the triple chevron. For those who are doing CUDA, of course, this is a piece of CUDA code. We are launching a kernel which will use this object, which for the moment, I would say is on the CPU side. The data, the content is on the CPU side. And now we are starting to execute the kernel on the GPU. And what we are doing is a page fault. And this has been, and this page fault is because still starting the Volta architecture, the GPU are able to handle page faults. And so we could implement this on-demand scheme. So you see that we have a data movement between an automatic, from the user application standpoint, we have an automatic data movement between the CPU and the GPU. And now the page we want to, or so a page in the sense of the Linux page. So the by default page is 4K. It's not we have moved a 4K piece of data from the CPU to the GPU. And of course, this data movement is done at the speed of the interconnect between the CPU and the GPU. And so what matters here for performance is how fast the interconnect could be. So it could be PCIe or it could be NVLink. And for those who are using the Cinica Marconi 100, I mean, the P9 are connected to the GPUs through NVLink also. So you could have a faster connection than the PCIe one. But okay, so this is the way this CUDA unified memory is working. And we have this feature since quite a time. And it facilitates a lot the software development on GPU. So what we will speak about today, just a step back. So you see that we are developing technology and we have this full stack applications where on the CUDA platform, we have this platform approach. We are developing a lot of software bricks. And today we will speak about the software bricks and the SDK regarding software development for the high performance computing and focusing on the language, meaning the compiler. So Our software direction. So first, if you look on the left side of this slide, so these are the three languages where we are investing a lot of money, I would say, for developing the software ecosystem, their software ecosystem. One is C++, of course. The other one is Fortran for legacy applications. So, and now a recent newcomer is Python. We start to see Python application. First, Python used as kind of scripting or upper layer on application, but now we are starting to see full application written in Python. And the question is how you could scale Python application. We could see what you could do using the NVIDIA ecosystem, software ecosystem. We are not forgetting libraries. Yes? No, I think there was a question. No, okay. So we are not forgetting libraries because libraries is a very useful tool. I mean, when it has been ported and developed on GPU, and you will see that we have a set of libraries we are tuning and tuning and tuning again. But the last direction is to have multi-GPU features and now also multi-node, multi-GPU feature. And we are not forgetting also to develop the ecosystem with our partner and for instance, with Raja, with Laurence Livermore, for instance, but with a lot of other partners, I mean, where we are cooperating to have their software running fast on our GPU. And we have, of course, some domain libraries, but this is a little bit out of the scope of this presentation for today. But like our quantum library, for instance, if you are interested by quantum computing. So the core of the SDK, which you are content and certainly you are using already today, is what we call the HPC SDK, which is including compilers, but a set of libraries for compute, for format, and for communication, including everything is packaged and everything is, I would say, is tested so that all those components, communication libraries, OpenMPI or NVSHMEM, are working with the compiler. So, and if we and of course we have profilers and compilers, programming models, and this is I would say programming models and compilers for implementation. This is the main part of the topic of today. So. And I will switch to the next slide just to have another view of what could you do if you want to port your application on an heterogeneous platform using GPU NVIDIA. And you have basically three ways. So, and the way we are investing a lot of time to develop the ecosystem is doing ISO programming. Well, ISO programming meaning we want to leverage the feature which are introduced in the language standard to parallelize your application. So, and could be for C++, and there is, we will see in the next slide, the extension. So, which construct you could use for having an application which could be, for which the source could be compiled both for the CPU and the GPU or the accelerator, meaning that you are keeping the single source branch or source code branch, but you could have different compiled, different binary or even unified binary to run on the hardware which is available to you. So this is this transform, for instance, parallel STL thing. In Fortran, we have this do concurrent, which has been introduced. So this is one way, and this is a way we are trying to advise to developers. So because they are developing, they are thinking about a parallel implementation, a parallel version of their application, and they have one implementation. Another way, which certainly you have used, is to use a directive-based approach. So meaning that this is since the end of the 90s, I mean, with OpenMP on CPU, more recently with OpenMP offload, starting with OpenMP4, those features which enables to program an application using an accelerator. And you have also OpenACC, which is another standard you could use. And those directives approach
Am I the only one not hearing anymore?
Oh, it's the same for me.
Okay, so I think we lost François. Okay, I can go in the chat.
We lost Francois, I think.
I think so, yes. There's something
we-
in the chat because he's still okay. Yeah, he will reconnect, I guess.
Maybe we can wait a few seconds. Otherwise, I will start with the hardware and then we will come back when he will connect again.
Sure. No, let's wait a few seconds. He just left the call, so I assume he will reconnect in a minute. Unless the incident is big on the laptop.
He lost power in his house. This is the problem of, you know, working from home.
So sorry, dear, all about that.
Okay, so what do you think if I start with the hardware and then
Yeah,
we will go
yeah,
back?
okay, yes, go ahead. Go ahead, let's do it.
Okay, let me share my screen. Sorry guys for this, but
Oh, that happens, you know.
that happened, yeah. Okay, so while we are waiting for
François just reconnect.
Francois is back.
Yeah, sorry. I mean,
No
I don't know. I mean, I lost the connection. In fact, I saw the here. So, well, I don't know at what time I have been cut exactly. I was just starting the directive-based approach, I guess. This was
Yes,
the last moment.
you were talking about the directives.
Yeah. Okay. So I will speed up a little bit because I'm not. I have to check the time. Okay. So you could.
You need to share. You are not sharing.
Ah, shoot! Yeah, I lost everything. Yeah, right.
For the time, no worries. I mean, if you want a bit more time, that's okay.
Okay, sharing. That should be. You see, coming back. Okay. Nice. And which? Yeah, I have this bar here. Shoot. Yes, that should be better. Right. Okay. So, sorry for the interruption. So you have also this incremental way of porting your application using directives, and you have here two sets of data directives.
Excuse me, I'm not sure you are showing the right screen. What I see is the presentation mode and not the full screen mode.
I did switch. Oh, sorry. Yes, right. What's the heck with that?
Yep.
Sorry. And now?
Yes, perfect. Perfect. Thank you.
Okay, sorry. Nice. Okay. So you may use directives, and you see here, but won't be the larger, I would say, simply to mention directives here at the point in time. I think you already have seen that in the past. And the last, if you want to have, or you expect to get more performance, if you need to specialize your code on using CUDA, for instance, here. And of course, they're taking advantage of libraries. So, yes, I know. So now let's see the slides with focusing on accelerated standards. So, and this is where we really want to spend some time. And starting with C++, and 25, 45, yeah, 20 minutes more. Okay. So here, if you see the evolution of the standard in terms of parallelization features you have in C++, the first thing, well, of course, in C++11, in C++11, you have seen the notion of thread for CPU with a change in the memory model for managing the privacy. But the big point for accelerator is started with C++17 with the parallel STL, for which we have an implementation, and we will see some example of that. But there are much more coming. I mean, with C++20, which has defined how to, which has defined a synchronization library, which for scalability and some other features. What is the pipeline, and for which we have a preview in our compilers? So with some features you could have activated. Sorry, I have to switch that. Is regarding how you could program algorithms in an asynchronous way, and a very important feature is the sender receivers. I mean, so that you could parallelize and you could organize a pipeline, asynchronous pipeline inside your application, and this feature which allows you to span over multiple GPU as well. And there are many more features, like the definition of data structure and the improvement of the memory model. So for data and dimensional array with MD-span, which is coming. And the an API also for using linear algebra algorithms. And to give you an example of what you could do today with, let's say, using standard parallelism, I will take one small example about using an hydrodynamic code, which is called ULESH, which is quite famous. And this is this mini application has different implementation. It's an open source implementation. It's open source, sorry. And you have various implementation: OpenMP, OpenACC, Cocos, CUDA. And you could compare then the efficiency of the different implementation. And here we will look at how this thing could be done using the ISO C++ standard. And this is summarized in this slide. On the left side of this slide, you see the implementation of, this is a pattern of the implementation, the OpenMP implementation. You see that you have those pragma, and you have to define some specifics, variables or arrays for OpenMP. And so, of course, in your implementation, one way to do it is to use ifdef in your implementation. And regarding the parallelization, you are using this parallel construct and the OpenMP4. So this is the way the code is structured, is implemented using OpenMP. If you want to implement it using the PSTL, and this is what is shown in the right rectangle, and here, oops, sorry, I have to move something, yes, here. You see this is much more compact, and we are using the transform reduce algorithm for that, because this is a combination of, this is a reduce operation inside, and we're using this transform reduce applied to this iterator. And you see that we have a much more compact and portable. The point is this syntax is understood and could be run on by any kind of compiler supporting this standard. Could be G++, could be ICPC, could be Microsoft compilers, so the CL compiler as well. And it could run either on CPU or, here in our case, on the accelerator on the GPU. So one question is, okay, I have one implementation, but what could be the performance over the different architecture? And here is to summarize this, and you are seeing the performance in here. This is a speed up with a reference, which is the OpenMP implementation on an AMD EPIC 7742 64 cores or ROM core. And you see in blue, this is the code compiled with G++, so the performance. And in green, the code compiled with the R compiler. And you see that using 64 cores as a reference, well, whatever the compiler here, we are in the same ballpark for the OpenMP implementation. Now we are using the C++, the standard C++ parallel implementation. And you see already you start to have an acceleration. So moving from 1 to 1.5, even 2 on 64 cores using our compilers, and using exactly the same implementation, you could parallel your application on the GPU and then take benefit from the power of the GPU. So one question you will ask, but okay, you started the presentation speaking about data transfer, and you know very well that the data has to be transferred, but in the code you showed us, there is nothing regarding transfer, of course, because when you are using this standard parallelism with our compiler, by default, automatically you will use the managed memory, the unified memory you have. And this is the beauty of the thing. So you have only to sync using the to use the standard feature, the standard parallel feature of the C++, and you don't have to think about the data movement. And of course, it's behind the scene. If the data exchange is done very quickly, then you are achieving a very good performance. So how do you, I mean, when you are handling, I would say, yeah, this is an example about handling, I would say, rather fine-grained parallelism when you have parallel for loops, in fact, a parallel section and you have 4 loops. So you have 2 ways, 2 iterators, two algorithms, sorry. Either you could use either for each or a transform one. And the point is, you could also combine, you have other more complex algorithms, like in the case shown, is you have a reduce inside your, so a reduce operation. Inside your parallel region, you could combine this transform with transform reduce, for instance, with the iterators, which give you this very compact syntax and very elegant syntax. So this is one way to code refactoring. And of course, I mean, when you are combining the transform and the reduce, so as you see here, you instead of doing the reduce inside the parallel region, you are gaining a little bit more of performance. And on this slide also, what is interesting is the efficiency of the parallel implementation of the GPU of this C++, those C++ implementations compared to CUDA. You see that you could achieve a quite significant fraction of the CUDA implementation, where in OpenACC and or OpenMP, you will achieve less performance because what you are using is the very well-tuned algorithm of the PSTL here in this case. And you see the difference between between what is running on the GPU and what's running on the CPU. So this is one way to do this development. So, of course, and this is some hints, but I will skip that. I mean, we could come later tomorrow for those who are coming with their applications about how you could use this unified memory. I mean, what are the guidelines to be efficient with? Exactly the same with ISO Fortran. So just to give you a little bit of what's coming in with Fortran. So with the 2018 standard, I mean, well, started with 2008, in fact, but has been improved in 2018. I mean, the do concurrent construct, so which could enable you to parallelize at the loops or loop arrays. Also, something important when you are using Fortran 90 array syntax is you could use have array intrinsics running on the GPU. So I have a couple of slides regarding those features which we are running. What happened in the next standard is the ability to have reduction into the parallel region defined by do concurrent. And this is something we have implemented already, which if you are using our compilers, you could use a feature. We are anticipating the norm, the standard, sorry. And what is in discussion and where we are looking at very closely is the use of atomics for in Fortran, and also asynchronous tasking, and in the same sense as the tasking in OpenMP. So just to summarize, today with our compiler, this is what you could do. So co-arrays, which is mentioned here, is something we are looking at but waiting for the Fortran 90 VFLang project to be really mature before to move forward, really. And give you an example for those who are, I don't know if there are still a lot of Fortran legacy codes running, but this is a small example regarding the use of a do concurrent. You see that here we are using do concurrent to, in fact, create and parallelize a set of nested do loops. In fact, we have two nested do loops where on I and J, and we are computing this operator. Computing A and B, and to use an example. And for with the advantage of this construct is at the same time, because of the syntax, you could collapse the loops. In this case of nested parallelism, and which at least automatically give more freedom to the compiler to optimize the syntax here. And you see that the same code is running both on CPU and GPU. And of course, when you are using GPU, I mean, you are taking advantage of the compute power and the bandwidth, the memory bandwidth on the GPU. So intrinsics, more guideline is for some intrinsics, for instance, for matrix multiply. I mean, this sort of intrinsics will take advantage of, or will run on the GPU, and even further, they will take advantage of specific alpha features of the GPU, which are the tensor cores, and they will use the compiler will use the CU tensor library to do this kind of computation. So matrix multiply is I would say a specific case of tensor multiplication. And using the using the standard of the language, using the intrinsic as defined, you will automatically use the tensor cores, and you will use in the best way the GPU. And here, this is to compare if you let the compiler parallel on the GPU. So sometimes we have seen developers rewriting the would say some BLAS library, for instance, for their application, which could be good for, I would say, which could be good because they are managing the whole software. However, for performance, I mean, it is better to rely on the language standard, and specifically the intrinsics, or which the language that the compiler is offering. And you see why, because the performance difference here, we are comparing the V100. This is a kind of CPU, the GPU generation you are using. If you are using the I would say the nailing line, so the work done by the compiler, compared to the intrinsics that you see, you have, let's say, 1 order of magnitude of performance. And of course, if you are using the 64-bit tensor cores, that's you have another speed up with the latest generation, with the Ampere generation, and of course with Hopper that you will be presented very soon. And of course, this is covering a lot of photon intrinsics. We'll skip this one. I will skip that. We could speak that tomorrow, for instance, if you want to see what is the approach. And anyway, we will give you let that into the presentation for you. And just to jump to the 2 examples, one is Milliweather. This is the one application. It's a CFD. It's a part of a weather application, which has been parallelized. It's a photon implementation. So you have a cold stream entering into this atmosphere, which is hotter, and you see, and we are interested by how the stream is developing and the turbulence, by the way. And so this is the code is presented here. The parallelized version of the code using do concurrent is presented here. And we are showing the different speedups, comparing the OpenMP implementation to the do concurrent. You see that we are on the CPU for the dual socket CPU. And here, with the do concurrent, the speedup, and you see that the OpenACC that would be the same with OpenMP offload, that the do concurrent is achieving the same performance level. So, but here you have only one implementation, whatever the architecture, CPU or GPU. And we have another example here, but here we simply to compute the solar magnetic fields, coronal magnetic fields, in fact. Where the do concurrent construct has been used. Fortran, Python, I will go quite fast. In fact, this time is flying, and normally I have 2 minutes left. The point to be productive in Python, and a very important feature is the ability to compose. I mean that you could use objects coming from used or built by other modules. But today, so this is the nice thing with Python. So and you see this is an example here. This is a conjugate gradient solver, and which is here. And the syntax is sequential. And by the way you express the computation, everything is sequential. And what you would do, ideally, you would like to keep is this sequential implementation, and the composability of the code. And this but now to benefit from the acceleration from a GPU, for instance, or to be able to parallelize. And so this is the big challenge with Python application. And how you could do that within the NVIDIA software ecosystem is, well, I would say that, shoot. A slide missing. Oh. Yeah, okay, so I have to switch back to this one. Is a project, and this is the a library, a set of modules we have developed, which is called QNumeric, which is a parallel version of NumPy. So simply, and what we have developed, and so you could keep, so the same approach when you are using NumPy and using this sequential semantics, but under the cover, so everything is parallelized on the GPU, and on the GPU, not only on one GPU, but this is where you have this picture here, on a set of GPUs, on multiple GPUs and on multi-nodes, multi-GPU. So, and in terms of performance, if you look at when you are using this QNumeric library, it's an application, so it's a deconvolution application here. So as you could see, we are still keeping the sequential semantics, but we execute in a parallel manner. And here, what we are looking at is the weak scaling of this application. And we were not comparing CPU to GPU, because already you are achieving a quite significant speed up on CPU, but we are comparing the one GPU speed using with QPy, which is also another but single GPU, I would say, implementation of NumPy with QNumeric. And you see that with QNumeric, you could scale on a large number of GPUs. Here in this example, we stop at 1,000, but we could have continued to scale as well. Well, another example of CFD, I mean, where we, and I will stop here because it's 2 minutes over my time. So if you have any questions, we could take them now or wait for the end of the presentation. Up to you.
Birol, if you have any question, please unmute. Okay, I don't see any. So thank you very much, Francois. I propose that you continue.
Okay, so I am the next speaker, and I go through some hardware announcement that you will see are very aligned with what we were doing on the software side. And the reason why we really started with the software part, the update on software part, is because our company, Nvidia, is moving very fast to be a platform company versus a silicon provider. And this is because we are not seeing that the traditional supercomputer centers are demanding new workload to run on. And these supercomputers will be connected with a ton amount of sensor that require some intelligence, some AI capability on the edge. But at the same time, they want to share the results through the cloud or running some of the workload on the cloud. And of course, at extreme I/O speed. And why that? Because I talk about age. I talk about the fact that, for example, we are working with other fusion community like ITER and UKEA, where they were looking to control and design the fusion vessel, including real or virtual sensor, in order to be able again to control the plasma in a way that is made only with AI. So Omniverse is the center of this discussion, and is a way that we can visualize in a very high photorealistic way the behavior inside the vessel, and at the same time create a surrogate of the vessel to control the path of the neutrons, create a surrogate that can be connected to our nucleus and modulus component of Omniverse, to the physics, to the different plasma software simulations, and software that are predicting the neutrons path. At the same time, supercomputer center are asking us to go beyond the standard model and simulation, and host domain-specific library like QQuantum for quantum computing. So there is a request of more flexibility in the kind of workload and the kind of connection a supercomputer has. And Nvidia as a platform is able to deliver that, is able to provide you all the software that Francois was talking about, and much, much more in terms of domain-specific libraries, in terms of Python support, in terms of AI frameworks, in terms of deep learning and machine learning frameworks. But all this software needed to be run on a very powerful device. And what we announced very recently is the Nvidia Hopper H100, that is our latest product. The H100 is not, as you would expect, 2x, 3x the performance of A100. Just because we are based on TSMC 4 nanometers node, and this is the first GPU on this process technology that enable us to have double the execution at every precision compared to the A100 per clock. So basically, each of our processor unit can deliver 2 times the performance. Then we have 20% more SM unit for each GPU, from 108 to 132. And then we can increase the frequency of the GPU by another 30% with up to 700 watts. So overall, you will see that at every precision, we can deliver 3 times the performance if you multiply all these factors together. But it's not only about flop performance, because we are implementing, and this is the first GPU that is implementing HBM3. So we improve the memory bandwidth by 1.1, 2 times the compared to the A100 to 3 terabytes per second. And also we implement more the possibility for threads to be more local, without going every time to the HBM memory. So this will bump even more the memory performance, the memory access performance of each single thread. We improved the L2 cache to 50 megabyte, 4th generation of NVLink, moving from 600 gigabyte per second aggregate bandwidth connecting different GPU to 900. We implement also confidential computing capability, so encryption when you run the GPU in the cloud and when you connect the GPU to a virtual machine. In this case, the hypervisor cannot access the memory data of the GPU. And so many innovation, many new capability, but probably the most important capability, and this is aligned with the strategy around Omniverse, and this align the strategy of in HPC and AI integration, is the new FP8 precision, combined with the transformer engine that allow when you run AI workload on the H100 to use not even half precision but FP8, and automatically the software, the transformer engine software, is converging to the same precision without any changes in the application. So a lot of capability, a lot of innovation. And this has a direct impact on training for surrogate AI models. We have a big bump in performance compared to the A100, and we have a big performance improvement in HPC application as well. Okay, and you can see here reflected in this simulation. And in the product, the H100 is already announced and will be available for general availability in the summer. I will show you some roadmap in the next few slides. And this benchmark has been done on early silicon, and you see the quality of the performance. So how H100 will be available on the market, and the first instances will be in the summer of this year, the end of the summer of this year, so very soon, with the 8 GPU AGX and the PCI card. Okay, the 8 GPU AGX is our standard factor with NV switch that are connecting in an all-to-all configuration 8 GPU. The PCI card is limited to 350 watt and will not implement HBM3 but HBM2E in order to be a more cost-effective and balanced solution. Even because we cannot put extreme frequency on the GPU as well, due to the limitation of the PCI TDP. Then at the end of the year, we will have the 4 GPU AGX. But I think the innovation will start with the availability of the Grace superchip. So the Grace superchip are 2 modules, is a different form factor, as you can see. Each module has one ARM SoC developed in collaboration with ARM by Nvidia, connected to a GPU that in this case is Hopper, our actual announced GPU, or another Grace ARM SoC. So definitely creating a 2 kind of socket superchip. And this will be available starting the first half of 2023. In 2023, we will have also the possibility to externalize NVLink to create a larger fully connected GPU domain, up to 256 GPU, and these have been already announced. I will focus a little bit on Grace Hopper Superchip and Grace Superchip, because I think this will be the biggest innovation that we are bringing on the market. Why? First of all, because this Grace Hopper Superchip is completely aligned with what Francois was talking about. Why? Because one of the problems that probably you are seeing in developing with the unified memory capability, and by the way, unified memory capability is not only available from Nvidia. Many of our competitors have a similar capability, but all of them we are facing a problem. The problem that is very portable, is very easy to develop, but has a big bottleneck. The fact that you have a PCI connection that is quite narrow. And you can spend a lot of time doing this transfer and wait for this transfer to go. Now, with this NVIDIA Grace Hopper Superchip, we have a chip-to-chip coherent interface. And this is the reason why we created this special module. And this module are tight interconnect with the two, the CPU and the GPU. Because the NVLink between the CPU and the GPU is a 900 gigabyte per second bidirectional pipe. And when you have this kind of pipe that is 7 times more powerful than PCI Gen 5, you can start to think that, well, I'm not paying anymore the price of the unified memory, and I can really develop with unified memory without big penalties. But on top of that, and thanks to this coherent interface, chip to chip, this platform will expose both the system memory and the GPU memory directly. So you can even use malloc. You can even use the Linux standard memory access to access from the CPU, the GPU memory. Okay, it will be a single address. So you can start to think to do out-of-core operation very easily and very efficiently with this platform. And again, this is very in line with our software strategy of unified memory, but also standard language, because there is no possibility in standard language as so far to do transfer, explicit transfer between host and device to host. Okay, you need to go into OpenMP or OpenACC to do so. So this a great innovation. Plus, as you can see, now there is no more 1-to-4 ratio. There are some of the exascale machine that has been recently announced that are really optimized for, you know, the best flops per dollar ratio, because they have 1 CPU every 4 GPU. And this is perfect if you run only HPL. But if you are, for example, like in the EUROfusion community, incrementally developing code from, you know, to be only CPU to be partially accelerated over time, and then move to the classical GROMACS VASP maturity of fully overlapped and fully optimized for GPU application. Well, when you are doing this process, you really still need a lot of scalar contents in your platform. You don't want to have just one CPU that is driving 4 or even more GPU that are so powerful. And in this case, the fact that we have a 1-to-1 ratio with 64 very powerful ARM core, every GPU allow you to gradually port application on GPU without losing much of performance. Because at the beginning of your process, you have very few part of the code accelerated, but you are still at the 64 very powerful ARMv9 core on this platform. Okay? But with this process, we can, of course, cover probably 60% of the workload on any open science supercomputer in Europe, in the world. But what about the remaining 40% of the workload and the other 950 small applications that are running? So in this context, we are able to provide a solution for that. That is Grace CPU only super chip. In this case, as you can see, we connect the Grace ARM SoC with another Grace ARM SoC with the same 900 gigabyte per second connection. So effectively, this platform will be programmed as a single super chip. We are basically 3-4 times the bandwidth of Intel UPI or AMD XGMI. You have one NUMA domain per die, and you are programming this as basically 2-die solution. So 144 CPU core across the module, 1 terabyte per second of this low power DDR5 memory technology. This is for us a breakthrough in 2023 because not only we can claim very interesting performance. Basically, we are able to deliver 2 times the performance compared to the actual best AMD Intel CPU. But in 2023, this product will be 60% less power hungry than any x86 solution. Why? The module itself has 2 SoC and memory included for a total of 500 watts. If you compare to any x86 solution that require 300-350 watt per CPU, plus 16 or 24 DDR5 DIMM, you are looking at 900 watts. So the comparison between 500 and 900 watts give you an idea how this platform will be optimized for power at the same probably peak performance of the best x86 platform in 2023. So we believe that this is a big innovation. We believe that this will be the best platform for conventional computing in terms of performance per watt in 2022. But as I said, we are a platform company, and we are also announcing and putting on the market innovation in the network. not only with increasing the capabilities of our NVLink with external NVLink at the end of 2023, but also with the already announced improvement in InfiniBand. InfiniBand now is not only a network capable of 400 gigabit per second with NDR, but also increase the density of any solution with the new Quantum 2 InfiniBand switch, able to host up to 64 NDR node port or 128 NDR 200 port. In this case, you can enjoy the higher density of this platform. And you know, with normal dual socket conventional solution in 2023, one NDR 200 is more than enough, and allow you to have a 128 node in full non-blocking configuration attached to a single switch. This is absolutely incredible and allow you to even lower the overall cost of your network with higher density. The smart NIC are evolving. We have the ConnectX-7, that is the actual NDR-based solution, again with NDR full at 400 gigabit per second, or NDR 200 at 200, but also we have the Bluefield DPU. The Bluefield DPU will be the really center of our data center, because it allowed you to have a powerful ARM, again, CPU, that allow you to offload not only MPI, not only part of the network traffic, but application. We have a similar to CUDA language to program this device called Docker. And at the moment, you can offload an hypervisor, for example, in the Bluefield 3. Or for HPC application, there are some activity like MPI tagging or all-to-all reducing that can be done into this card. So we believe that DPU will increase the capability of a data center, increasing the security and improve performance. And then we have our Skyway gateway to connect InfiniBand to Ethernet, and our tools to monitor and troubleshoot the network. So at this point, I leave the stage to Filippo to talk about ARM, how ARM is important for us.
Thank you, Gabriele. So I share mine. Should be able to see the screen. So I spend the next, I would say, 15-20 minutes to give you an overview and an understanding about what we're doing in the ARM space, especially in the area of software enablement and the work toward getting ready from when Grace will be in the end of our customer partner developer. And during this presentation, I will essentially cover three main topics. I will give you a little bit of overview, very high level, very quickly about ARM and HPC in general, because, you know, obviously this is something that was going on for a while, and Nvidia has been, and we're very honest on that, we have been capitalizing on the work that many have been doing before us to get to the point when ARM is actually ready for HPC. We'll talk a bit about the focus that we're putting on enablement and the ecosystem software, which is key, obviously. Hardware is one side of the coin, then the software is the other. And then a little bit of literally a few slides around what actually means porting on ARM today. At the end, there is a bunch of resources, and when the slide will be available, you'll be able to see additional material that is already been published online. So let's start with ARM in HPC. So first of all, it's very important to say that the journey of ARM in HPC has not started yesterday. So I've been very fortunate to following the evolution of ARM and how ARM moved into the HPC space. And I remember the time where people started to play with 32-bit ARM SoC. That was basically the same SoC in a mobile phone. So they were talking about more than a decade ago. And people already started to move interest into ARM because ARM was essentially a good value proposition in terms of performance versus energy efficiency and power consumption. That was one of the key strengths of ARM and one of the things that attract people and researchers and people involved in European project to look at this alternative for the future, a future that we'll see today, the idea of deploying per exascale and exascale machine in Europe to run big science. And, you know, things evolved. There were players, then appear and disappear. ARM v8, so the 64-bit start to happen and start to be implemented in silicon. And there was also a set of European projects. Mont Blanc was probably the most iconic of them, that in various series moved from proof of concept to the deployment of a demonstrator based on what was the time the Cambium Thunder X2. And it's key, the key message here is that not just that it started like 10 years ago, but also Europe has been probably the most enabler in terms of R&D project, hardware deployment and software development to pave the way for ARM in HPC. Now, until I will say, until 2018, things were interesting. And ARM has always been perceived, I'm honest here, as an R&D demonstrator type of project. From 2018, when ARM released the Neoverse IP roadmap, things literally took an exponential path. More commercial player, more ISV, more cloud provider, seeing the value of ARM, and they acquire IP and decide to look to build or embed ARM-based solution into their infrastructure. And so we saw bigger player building ARM SoC from Huawei, from AWS, from Marvell, from Broadcom, Ampere Computing, et cetera, but also the cloud like AWS and Azure by adopting what Ampere Computing is developing, see ARM being a valuable option to run the workload in the cloud. And we've been part of the journey too, because back in 2019 at supercomputing, we also started to move first path toward coupling ARM-based CPU with our GPU. And obviously, in the last few years, we saw the top, you know, Fujitsu with A64FX have been able to place an ARM-based system at the top of the top 500. And this machine has great characteristics and it's been there for few iterations of the ranking, both top 500, green 500 and others. And in Europe, we started to develop through Cyper and through, again, European project ecosystem, our own European-led based solution by Cyper. And obviously, we announced Grace, as Gabriele mentioned, in 2021. Also, there are a lot of farm-based systems around the world. This is a snapshot that I've been able to put together by looking at public data of institutions that have at least 10 to 16 nodes or more of an ARM-based system deployed in production. In UK, where I'm based, there is the Catalyst program that deployed 3 systems between EPCC, Leicester, and Bristol. There is GenC in France. There is the Barcelona Supercomputing Center in Spain. There is the University of Rothenburg that use QCD type of things in Germany. But then if we go abroad, there are the usual DOE labs in US, but there's a lot of also Japanese institutions where obviously there is RIKEN that is the most famous. And as I mentioned, we already pioneer or say bundled together an ARM-based CPU plus an Nvidia GPU solution in that case was the Marvell ThunderX2 CPU plus NVIDIA V100 and showcased a supercomputer in 2019. So we were interested in how ARM was evolving already years ago. At that point, we already have a line of product, but there was an embedded space based on ARM IP. It was just a matter of time where we continue to expand on our ecosystem present, but as well as building our own, that is essentially the Grace Superchip. So hardware, Gabriele spoke about it, more detail about MicroArc and things like that will come as soon as we become more close to the availability to market. But the question that everybody is asking, the question that everybody cares about, other than the hardware specs is, okay, that's nice. How do I actually run my software? And often, because we are a platform company, because we sell GPU, but also talk and work with developer, it's not just about how do I run my application, but what about everything else in between the hardware and the application level? So the ecosystem really goes end to end, and we are tackling and handling this as a complete, let's say, problem. So I would say that our objective, our goal is to achieve what everybody has been saying for a while, that broadly speaking, the ecosystem just work. That means that most of applications will be able to recompile and run out of the box. There will be a choice of multiple compilers. And the open source community will continue to maintain, develop, verify codes, not just on the legacy x86, but also on ARM-based system. Through CI/CD, through just software best practice. A thing that also happened in the past few years, which enabled this just work idea, is easy accessibility to ARM-based system. So maybe you cannot buy a server to put in your garage, which is fine. It consumes kilowatts, that's okay. But you can buy, a Raspberry Pi or a Jetson Nano or a Jetson Orin or other ARM-based ATX style type of boards that are actually a very good development vehicle to scale out then to real, big HPC-like type of system. And just work as a different level of complexity if we look at different level of the application layer. So obviously, I believe the most complicated one are probably the deep learning framework, because there's so many dependencies, so many things that have to move and be glued together. And in that space, we are working also to containerize the solution. So for user, at least for user, they would just be able to, Docker pull, Docker run, that's it. HPC application, it's a matter of recompile and run, but we also have to look at the library. And most of this library do already have some ARM, let's say, specific path, specific optimization. Other don't need it, just need to recompile and run out of the box. By the way, always opportunity to tweaking in terms of performance. We are really now be able to say, I actually be able to run something. And there is a broader category of that are very important nowadays that maybe, I would say 10 years ago was not that obvious. That is the general compute side of things. Today, science is not about my monolithic Fortran application anymore. It's a broad case of complex workflows that allows pre-post visualization, scripting. So all these things, mostly thanks to the cloud actually, because this is the general compute things, are already able to go on ARM and run without problem. Application-wise, this is a list of applications that we as NVIDIA have seen through ourselves or through our partner. But there are way more out there that I'm pretty sure has been tested, or if are not tested, someone will try at some point and figure out if they run or not. And we'll talk about why sometimes may not run and how to solve this problem. There is a column here about ISV codes, commercial ISV code, which is very important. Now, HPC is used in open science, is using to tackle fusion research. It's also used to, to design the car you drive, the train you ride, the airplane you used to fly around before COVID. So there's a whole set of applications that are really commercial, used in the commercial space to produce, often in the CAE and ADA and CFD. Now, it's true that commercial applications often catch with new technology at a later stage. And often it's not a technical problem, often is a business problem, because you need to have solution up there, need to have customer demand, they need to have also bandwidth to support a solution if their customer have a problem, so they have the proper support structure in place. So there are a series of and you can Google it, because there's a series of open statement and public open statement about specific ISVs started to support in some capabilities R-based system, and I mentioned some names here because they made some public announcement. But there are other ISV that are more shy, or they cannot share for multiple reasons. And what we often suggest as NVIDIA is that you customer as the best line of communication with this ISV, because you are their customer. So often they share with us, but they're probably going to share with you as well. So if there is any commercial code that you care about, that you don't know if it's work or not on ARM, my strong advice is that to reach out that ISV and ask explicitly. By personal experience, they are very eager to share if obviously you are one of their customers. This is the top layer of the stack. It's important to look about everything else, and we're really looking at absolutely everything. So application, we talk about it. We're looking at developer tools. So obviously we have our own. There is already tools that are enabled for ARM, like the ARM Linear Suite, Total View. There are also open source projects, often developed in Europe, for performance studies and performance visualization and supporting developers that are already enabled for ARM. There are obviously communication libraries. We contribute in some of those directly. Others come from our partners. Compiler, obviously we have our own. Francois already spoke about it. We are a contributor and a supporter of Flunk, so LLVM based. A little bit less to GCC, but obviously we follow their development, and we hope that they pick up the very latest innovation in ARM as quick as possible. ARM itself has its own compiler and performance libraries, which recently has been finally released for free to everyone. And obviously, if you have specific silicon, usually specific vendor build the compiler for the specific silicon. Libraries, plenty of them. Obviously, there are different level of library, more low level, like the BLAST, the FFT, more complex, like like PET-C or Trillinos or things like that. Very important things that we actually cares a lot is the enablement on the file systems. You can have as much computer as you want, but you need to have storage to have an HPC system. Otherwise, you do nothing. So we've been following obviously the enablement of Lastre, both in the open source space and both some of the commercial implementation. BGFS literally recently released a white paper a few days ago about how to deploy it on an R-based system. PanFS from Panasas. A lot of people are asking about GPFS, so it's no secret that IBM is working on it, but reach out on IBM to have a clear timeline. Spectrum scale, not GPFS, sorry, will be supported going forward. It's just a matter of time. Everything else is management, middleware of the system. Scheduler works, cluster management tool, we have them. Container is not a problem. Operating system, we're working very closely to make sure that the latest patch and the latest enablement will go to the mainstream OS release. So everything will be there from day zero. And we welcome, this is very important, we welcome also the more broad ecosystem development around ARM, meaning that we are developing our own CPU, but we will be happy and we will continue to be supportive of any ARM silicon provider that wants to bundle their CPU with our GPU. We announced during IESC our partnership with Cyper, so that's very important for us. AWS has been announced on Graviton 2, one of their ARM-based SoC, that they have the T4 NVIDIA GPU. So the more the better. Obviously, the dev kit that we talk soon about, it's not our CPU, it's Ampere Computing CPU. So we want the ecosystem to be as broad as possible, and Grace be part of it. We're also enabling as many OEM as possible to go to market with ARM-based solution coupled with NVIDIA GPU, obviously with Grace, but also with other CPU. And then we are getting very serious in participating in community activities like the ARM HPC user group, both hackathons. So you will see more and more NVIDIA people presenting and talking about what we do in this space on big conferences or on venues when the ARM, the ARM family, say, gets together. From a pure software that we maintain that is used not to program the CPU, but to offload on the GPU workload, we have the Nvidia HPC SDK. Everything on Nvidia HPC SDK is supported on ARM. Certain things, like the one that is highlighted in pink, are not fully supported on a specific platform like the dev kit, mostly because of its architecture, but for future Grace plus Hopper system, or for a different node architecture of a ARM CPU plus GPU, also NVMe and GPU Direct will be fully supported. Functionally, they work. The performance is not where we want to be purely because of an architectural choice. But this is good because that means that if you are adopted NVIDIA HPC SDK, if you already have a code that is, use the NV40 and NV C++ flags, you don't actually need to change any flag to rebuild on ARM. You just move to an ARM-based system, you recompile, and it runs. This is the whole idea. The experience from a user and developer perspective, because of the tool, from a CPU plus GPU kind of workload, will be basically the same. It should, ideally, the developer might not even realize that he's on an ARM-based system. That would be the ultimate goal. To start to seed and build the ecosystem, mostly with the objective to identify gaps. So to working with the community to identify something does not work. We put together a program almost 9 months ago called the NVIDIA ARM HPC Developer Kit. And we seed and be able to position some of this kit in several places worldwide, including at the PFL. So Gilles managed one of these nodes that will probably be able to be accessible by the EUROfusion community. And the idea of this system at the very beginning, that was almost a year ago, was designed to have a fairly accessible, both economically and both from a form factor point of view, platform that allow to experience 3 major components where NVIDIA is betting on. So an ARM-based CPU, not our at the moment, but still an ARM-based CPU, the NVIDIA GPU, which has been doing for 15 years, and also the NVIDIA Bluefield. Obviously, we know how to do GPU programming. We know that there are GPU codes out there. We encourage people to try to move their code on GPU to be more energy efficient, more performance, and things like that. We want to identify gaps. We want to handle these gaps as quick as possible in preparation of Grace, but also for the broader ecosystem. And so it's good to test things on CPU only, even if it's not our CPU. And the DPU, the data processing unit, it's really a new thing. I believe will open a very interesting new use cases. But it will take some time to, to understand exactly its value proposition and to make it, mainstream worldwide. That platform has some limitation. Our partner Gigabyte already designed a different platform, which is obviously a little bit bigger, a little bit more expensive. He has a GPU. He solved the problem of NVLink because he has a HGX platform that has been announced not long ago, probably just before Computex as well. And this is designed for more AI HPC workload. And this will be, and both are actually supported platform. So as I mentioned, we have around 100 dev kit worldwide deployed, usual names all over the place. EPFL is one of them that has one or two kits in-house. So how all of these map to Grace? Well, all the work we're doing is builds on what is ARM and its standards. So there's, commonize an ecosystem that allows to move from one CPU to the other. From a pure platform perspective, the idea to have the ARM server-ready certified platform. So Grace will be built not as a custom microarchitecture, but as a general purpose core from ARM Neoverse. And we see a lot of people, a lot of cloud providers embracing ARM. We expect some of them to also embrace on Grace. And then obviously we're working to have and build and expand the rich ecosystem. All the work done so far in 10+ years, especially all the work that NVIDIA is doing now through the dev kit and this initiative, will allow to have Grace production ready from day 0, which is extremely important. But where we're putting our focus, obviously, as a company, we don't have a million people working, a million engineers. We wish we solve a lot of problems. We need to be a little bit of laser focus about where our engineering are putting our effort versus where we support effort that coming from the open source community or from the domain expert, for example, in the case of EUROfusion. So in this particular moment in time, our priority is really to enable compiler and libraries, getting them ready for grace. And we welcome any feedback on the current status of compiler and library in order to make sure that when ACE arrives, it's top notch. We also focus on make sure that through our partner, reliability of support of file system is key. And then everything else comes, not say secondary, but comes as a direct effect. So working on enabling application, pushing more OEM, ODM to adopt platform. So to believe essentially that ARM can be the future, can be it's a valuable solution for the future. And obviously working with the developer tool, especially understanding what the developer experience should be when we couple ARM, when we use ARM CPU, also when we couple ARM CPU plus an NVIDIA GPU. So we announced also, it's very important because Gabriele mentioned about that, the dev kit is going to be a key important platform for at least another year and a half, but then Grace will be generally available, and there will be design reference for rapid adoption, both with Grace super chip only, so CPU only system, and both Grace plus Open. So how, just to wrap up, what's actually important to ARM today? So because there are few challenges because of the way we've been writing legacy software in the past, tens of years. So first of all, it's true, this is true, but a lot of people say that more often than people expect, porting to ARM is actually boring. I'm saying porting, when I say porting means my application compile and run and execute correctly. It doesn't reach the peak of whatever hardware I'm targeting. In HPC, we're always tweaking the application for the platform we're using, always fine-tuning, always optimizing. But porting and enabling to run is actually a boring task, and many people have been proven and say that, and so far this statement holds. However, sometimes it happens. So the cycle of porting application to ARM is no different than porting any application to GPU or to CPU. If I have a way to reuse, so to access container, access tools that automatically build, go for it. If there is no this way, take the source and recompile it. There are plenty of compilers. Some compilers can be better than others based on the code and how the code is written, but there is a choice there. When you run, then you figure out that, because of high core count, because the way thread per process can be mapped differently, because of the way the memory subsystem may work, there is different way you can run efficiently on our platform, but this is very much platform specific. There's not a single recipe that solves them all. And then there will be there are already tools to optimize, to dive into the CPU side or the GPU side, or how they are working together. So from our perspective, especially if we target AI workload, NGC will be a must-do. Solve the problem of headaches to deploy plenty of software, plenty of TensorFlow, PyTorch dependency, and also reuse some of those in a shared system with multiple users. But we are actually paying a lot of attention on tools like EasyBuild and SPAC to make sure that ARM works, our compiler works, our SDK and our library works, and things like that. We realize this is very important for the community and for the people who maintains and prepare the environment for the user at the HPC sites. Compilation tips. There are some specific flags, especially if you go on the GCC. Often when you target the native, takes the right choice by itself. If not, this is a bug to flag to the GCC or LLVM folks. The Nvidia HPC SDK, so our Fortran MVC++ compiler, often detect the architecture automatically. So without the need of a flag, you move from x86 to ARM, and you should pick up the right one straight away. Now, there are codes, unfortunately, that for many reasons have baked inside the code base some specific things that are vendor specific. We're not talking about a programming model here, but we're talking really about things low level like intrinsic or assembly, or assumption that because it works with iFort, then it has to work all the time. So it's important to try multiple compilers. It's important to be able to make sure that the code works everywhere. some compiler, and sometimes it's our fault too, are a little bit loose with the specification of the languages, allow you to do things that are actually not the standard. So it's important to check that. Make sure it runs with multiple compiler. On ARM case, because ARM is evolving and more CPU are produced, it's always better to have the latest version, at least 11 plus version, where the latest patches to generate efficient code or to support the latest CPU has been added. It's kind of obvious things, but I personally see a lot of old compiler because come with the OS installed on HPC system, and often users just pick that up because it's the default. It's good to try to do the modern things. Beware of non-standard build system. I mean, this depends about how people write the code, but sometimes they hard-coded things in, you know, in the autoconf, in make files. It seems silly, but sometimes it happens. And non-skilled user or user that don't really want to play with the code stops at that level and say it doesn't work. It's really very simple things to fix. And exactly, and then the non-default compiler is the same consideration about trying multiple compiler. The other big problem that is not always, it's a little bit more complicated to solve sometimes, is about what if my code has assembly or x86 intrinsics baked in it. So because we are in the high performance computing, we've been pushing the idea of optimizing no matter what, up to the very last. I want to squeeze the flop to the very last moment, very last bit, you know. This is great, but often introduced big hardware dependency on the CPU side that then become difficult over time to move from one platform to the other. Stickiness, let's call it in this way, that can be easy to handle. Now, there are libraries, tools that allow to do translation. So translate, for example, AVX into Neon, that is one of the ARM SIMD extension. I'm not aware about one that translates into the SVE, but there are probably, if you're looking for those. The reality of header-based or tool translator is that they never do a perfect job. It may be able to get you to work, but definitely not to the ideal scenario of decent or even good performance. Ultimately, if you are in the scenario where you have intrinsic and you need intrinsic, you will have to write them. So there's no magic bullet. There's no, you know, magic does not happen by itself. Someone will have to basically write the code. And luckily enough, because of SV characteristic to be a scalable vector extension that is vector length agnostic, writing actual SV assembly is actually easier than x86 assembly. The instruction set is not small, but the thing that people can use as a first iteration is not as big as AVX. And ARM itself, and we will contribute in there too, they have very good guidelines about how to code, if it's really strictly needed, how to code using intrinsic and assembly into your code base. I would personally suggest not to do it because of the way SV works. I would suggest that to try to rely on compiler auto-vectorization. Okay, someone is going to tell me, oh, Filippo, it doesn't work very well. You know, the compiler does not understand what I'm doing. Okay, this has also happened. Compilers often are stupid. If we don't know where the problem is, we can't fix it. So if we find a problem around vectorization, we want to know, at least on our compiler, we can fix it. And only go to assembly and intrinsic if you really want to cover the last mile, the last 1% of performance, the last 5%. And with this very simple, but some, I believe, obvious guidelines, you will have a code that is portable from x86 to ARM, but also between different ARM SoC. So, as I mentioned, there are a few useful resources. The slide will be shared, but we have plenty of GTC session covering the ARM topic this year and the last GTC fall. There is GTC fall coming this year as well after the summer. There might be ARM-related content as well. So keep an eye on our normal communication and outreach channel because more material around ARM is coming out. Work done by us or together with some of the partners. And this is some of the link, as I mentioned, will be left as a reference. If there is any question, I'm happy to take.
Thank you very much, Filippo, for your talk. Guys, any question? Okay, I guess it's a no. So correct me if I'm wrong, but I guess that concludes our webinar for today. Again, thank you
Yes.
very much for the presenting of this very complete roadmap. I think it was necessary and useful for EUROfusion people. Is there any other discussion or question you would like to address, guys? Okay.
So just one comment, Franz, from my side. Obviously, as I mentioned, there is a one ARM HPC dev kit at the PFL. Gilles manage it. It's Gilles machine. Gilles do whatever he wants with the machine. But I hope that machine will be accessible by all the EUROfusion community, scientists and developer, because through a PFL engagement, but through an EUROfusion engagement, we can help, if any help is needed, because maybe not, to experience and have a positive experience on ARM-based system in preparation for Grace.
Sure.
Yeah, so we have one, we installed one, and we are going to receive a second one. We now just have to see how we can share access with the EUROfusion community, but yeah, it should, we should be able to give it to give access to the EUROfusion community. Yes.
Thank you very much. So the pressure is on you now, Gilles.
I will say that. But if there is any problem, we have also some cluster with ARM available for external access. So we could give access as well. Okay. I think Jensen, our CEO, has really put pressure on us to enable the ARM ecosystem and to make as much as possible available for developers and resources in this respect. Thank you, Franz, to hosting us today, and looking for the session tomorrow.
You're very welcome. Thank you, everyone. So see you tomorrow for some of us. Bye.
Thank you. Bye-bye.
Bye.
Bye.